Now we are going to give a description of the proper rotations in 3 dimensions. Let's just remember this. Any improper rotation, let's say it like this, x is improper. Any improper rotation can be described as inversion followed by a rotation or vice versa, doesn't matter. So J is the inversion in here, inversion operation, and R is a proper rotation. Once we understand the proper rotations, by using this relationship, we can also say something about the improper rotation. So that's why I'm concentrating on SO3 in here. So it's just the description of the rotations. So as a result, I'm going to assume that R is a proper rotation. Proper rotation in 3 dimensions, which means, of course, the determinant of R is equal to +1. So, so the next question that I'm going to ask is this: what are the eigenvalues of R? So this is going to give us a lot of information about the corresponding rotation actually. It's not a question that we usually ask when we are met with a matrix, but this is going to give us some geometric information. So I'll say something about the eigenvalues. So let's just start with some of the things in here. So first, we have to realize that, of course, the eigenvalues of orthogonal matrices have modulus 1. So that means if lambda is an eigenvalue, that means that this absolute value in here is equal to 1. So just remember that this is modulus. So this thing is essentially equal to the square root of the complex conjugate of lambda multiplied with lambda. So in any case, this implies that lambda is a number on unit circle. So on the complex plane, we have this unit circle in here. That's the x and the real and the imaginary parts of the complex numbers. So as a result, this is a complex number on that unit circle. How do we do this? How do we understand? Well, we just write down the eigenvalue equation like that. Let V be an be the eigenvector. For a complex eigenvalue, of course, the eigenvector has to be complex, so we have to take this into account. So what we do is we just take the Hermitian conjugate of that equation. So as a result, I can write this equation like this: V dagger R transpose, that's equal to the complex conjugate of lambda times V dagger. And then I take the product of these two equations. So we have V dagger R transpose R V, that's equal to lambda star lambda times V dagger V. Let's remember that this is identity, so as a result, on the left-hand side, I have the inner product of V with itself. On the right-hand side, I have the modulus square of the eigenvalue, and then V dagger V. And since the eigenvector is non-zero, this is non-zero, so therefore this cancels. So as a result, we get this lambda squared is equal to 1. So this shows that the eigenvalues have modulus 1. By the way, this is in general true for any unitary matrices. Let's remember that the orthogonal matrices are unitary matrices with real entries. So this is in general true for unitary matrices. So there's another property actually, that the eigenvectors corresponding to different eigenvalues are orthogonal to each other. But at this point, we don't need this. So we are going to say a similar thing for by using a different geometrical argument. So next thing is that if we have an eigenvalue of R, so let's say that lambda is an eigenvalue. Lambda is eigenvalue of R. This implies that the complex conjugate of lambda is an eigenvalue, is also an eigenvalue. So if lambda is real, of course, this doesn't give us any information. But if it is complex, then this gives us a new information. Why? Because the characteristic polynomial in here, so this is the determinant of lambda I minus R. If you think about it, since R has all real entries, this is an equation where all the coefficients are real. Whatever, I mean, we have this kind of an equation in here where all the numbers are real in here. So as a result, if lambda satisfies that equation, then lambda star also satisfies the same equation. So because the coefficients are unchanged. So let me not write the same thing in here. So therefore, this is one other requirement. So for any real matrix, basically, if there is an eigenvalue, then the complex conjugate of the eigenvalue is also another eigenvalue. And the product of the eigenvalues is 1. So that means, of course, if lambda 1, lambda 3, lambda 2, and lambda 3 are eigenvalues, I mean, R should have 3 eigenvalues. Then we know that, of course, the determinant can be expressed in terms of the eigenvalues as the product of the eigenvalues. Since the determinant is 1, therefore the product of the eigenvalues is equal to 1. So these 3 mathematical relationships actually gives us some information about what the eigenvalues can be. So as a result, I'm going to do this. What are the eigenvalues? What can the eigenvalues be, right? So as a result, I'm going to make this analysis in here. So what can the eigenvalues be? Eigenvalues of RB. So there are these 2 cases. So R has an eigenvalue that's complex, has a complex eigenvalue. So let's say that R has an eigenvalue in the form of e to the I theta. So that means this is our first eigenvalue, where I mean, this is on the complex plane, not on the real line. This therefore implies that a second eigenvalue is given by e to the minus I theta. So this is different than e to the I theta. And so therefore, because of the product of the 3 eigenvalues should be equal to 1, and the product of the first 2 eigenvalues is obviously 1, therefore this lambda 3 should be equal to 1. And so therefore, in that case, the eigenvalues of R should be, there is an eigenvalue 1, and an eigenvalue e to the I theta, and eigenvalue e to the minus I theta. So that's the first case. If the rotation matrix has a complex eigenvalue, then the eigenvalues must be of that form. There's a second case. R has real eigenvalues only. But in that case, I mean, since the eigenvalues should have modulus 1, and only real modulus 1 numbers are plus and minus 1. So in that case, there are these 2 possibilities that the eigenvalues of R can be either 1, minus 1, minus 1, because their product should be equal to plus 1, or can be 1, 1, 1. So the minus 1 can be should appear an even number of times. So as a result, these are these 2 possibilities. So in any case, that's the result that I'm going to use. Let's just do this. So the last case, this case corresponds to a matrix where the only eigenvalue is equal to 1. All eigenvectors have eigenvalue 1. And this essentially implies that if the eigenvectors are linearly independent, if there are 3 linearly independent eigenvectors, this essentially means that the operation is the identity. Right? The rotation is identity. So that's a very trivial case. The second thing, this special case where the eigenvalues are 1, minus 1, minus 1, in that case, I can write minus 1 as e to the I pi. Well, it's as a complex number, it basically corresponds to the angle pi. So let me just draw the unit circle somewhere in here. Right, this is the unit circle. Let's say it like this. This is the number 1 in here, and that's the number minus 1 in general, and a number with angle theta is e to the I theta, you can see that the number -1 corresponds to the angle 180 degrees. So therefore, -1 is equal to e to the I pi. So that's also called the Euler's relationship, because this is a very nice relationship. In any case, so therefore, I can actually describe this as the eigenvalues as 1 e to the I pi and e to the minus I pi. In this case, this is basically is a special case of this one, except that the other two eigenvalues, the last two eigenvalues are now real, but reality has no special meaning in here. So as a result, in that case, I can summarize the result like that. So let's say it like this. If R is a proper rotation which is different than identity, then the eigenvalues are 1 e to the I theta, e to the minus I theta, where theta is now strictly positive, but less than or equal to pi. You can actually think of it like that. So as a result, we have this kind of a situation. Let me erase and redraw this picture again. So forget about this -1 in here. 1 is important. So the eigenvalues are, this angle is theta. This angle is also theta. So the eigenvalues are e to the I theta, 1, and e to the minus I theta. And there's a very special situation where these two eigenvalues might coincide at this point. Both of them can be -1. Or if you want to include theta equals 0 as a case, too, we can also include it. There's no problem with this, in which case the R can be equal to identity. So all three eigenvalues are in here. In any case, so there are actually one important conclusion in here is that one of the eigenvalues is equal to 1. So basically all orthogonal matrices has an eigenvalue 1. If the orthogonal matrix, all proper orthogonal matrices have an eigenvalue 1. All proper ones. For improper ones, that would be -1, but in any case, that's something else. What else? So that means, except identity, of course, except identity, this eigenvalue is unique. So therefore, there is a unique eigenvector for it. So, but for identity, of course, we cannot define this eigenvalue uniquely. So therefore, all vectors are the eigenvectors. So in any case, so that's the situation if the rotation is different from identity. Sorry about that. There is a unique direction. So I'm going to show this by n hat such that R applied to n is equal to n. So that's basically the eigenvalue equation. So there's an eigenvector such that, this is satisfied, such that the eigenvalue is equal to 1. That corresponds to that. But from the geometric point of view, now we can interpret this as saying that there is a vector where this rotation does not change it. So because of that reason, we just call n as the rotation axis. Right. So we just call this as the rotation axis because this is a direction where under rotation it doesn't change. So we will basically describe, so n is a vector in 3 dimensions. So we will basically describe the rotation as a rotation around this vector by an angle theta. So this theta also has this rotation angle meaning. Right. So as a result, this properties of the eigenvalues basically enables us to describe this. So I'm going to say a few more things about the rotation axis. So it's kind of obvious that since this eigenvalue 1 is unique, this n is a real vector. You can choose it as a real vector. So there's just a unique direction where this property is satisfied. So n is a unique vector. I'm going to make it normalize so that therefore n is a unit vector. We can always do this normalization in here. Apart from that, there is no difference between plus n and minus n. So there are these, let's say it like this, both plus n and minus n can equivalently be described as rotation axis. Actually, an axis is a line without any direction. You can actually think of it like that, but we would like to give a direction in here. This kind of tells you that there are actually these two equivalent choices for choosing that direction. I can choose it along that way or the other way, but in terms of the mathematical description, both of them would be equivalent. All right, so let's just keep this in mind, because this is a point that that's going to come out later. So this is an important part. Okay, so next, let me forget about this because I need to redraw this. So we have a direction in here, n. So suppose that we have a vector v in here, which is perpendicular to n, let's say. So consider the rotation of that vector. So basically, I'm transforming vector v to v prime, which is obtained by applying r to v. So since n prime is equal to n, so after you rotate n, you get the same vector. This kind of tells you that the angle between these two vectors should still be 90 degrees. Right? So that means we have a v prime in here. We have a v prime in here, where that angle is also 90 degrees. So therefore, think about the plane which is perpendicular to n. So let me call this plane as P. Right? P, plane perpendicular to this rotation axis. So in that case, R transforms vectors in this plane to vectors in P. So essentially, in that case, R is essentially a rotation within that two-dimensional plane P. So as a result, you can think of this rotation R as an element of SO2, but for that two-dimensional plane. So as a result, since that's also a proper rotation, okay, and let's remember that from what we have seen for the rotations in SO2, a rotation by theta would basically have eigenvalues e to the I theta and e to the minus I theta. This would then imply that, of course, within that plane, the angle of the rotation is theta. So I'm just going to make this justification. Apart from that, I'm not going to do any proof that this eigenvalue in here, the theta that appears in the eigenvalues, is the vector, is the amount of the angle. But it has to be obviously so, because a rotation in 3 dimensions is essentially a rotation in 2 dimensions. There's just an added arbitrariness that the axis of the rotation can be arbitrary in 3 dimensions, right? That's the only complication, right? So as a result, I'm going to be content with this. So apart from that, what else can I say? We can then do this. So I'm just going to, all right, I'm also going to talk about this directions in here. So there's also arbitrariness in the angle theta, because I cannot distinguish between basically a rotation by plus theta and minus theta. Think of it like this. Let's say that my axis is n, and I have a rotation in here where this vector is transformed to that vector v prime, and where that angle is theta. I'm going to assume that theta is small. Let's say that this is 45 degrees. Okay. So basically, if I look at this picture from this point of view, this is my eye, let's say, right? From my eye, I'm just looking at this picture. In that case, the vector n is going to be a vector which is pointing towards us. Vector v is like that, and vector v prime is like that. So that's basically a rotation by a positive angle. But we have said that I can also describe the rotation axis as minus n. So as a result, I can look at the picture from this direction. So from that direction, the picture is going to look like this. So minus n is pointing towards us, so that's minus n. Let's see, the vector v is going to point out like that, and then vector v prime would be pointing like this. So as a result, in that case, I would describe the rotation angle as the negative 45 degrees, for example, minus theta. So as a result, depending on how you choose this axis n, you can describe the rotation angle as positive theta or negative theta. But we should have a convention for the how we choose for the amount of the angle, right? And it appears that there is a nice convention, and that's the right-hand rule, right? I'm going to do it like this. Right-hand rule. So I'm going to do it like that. So that's the picture of my right hand. That's not a nice picture, but doesn't matter. So if I am choosing my rotation axis like that, then the other four fingers show the positive direction for theta. Direction for theta. You can think of it like this. So coming back to that, so as a result, if I choose my axis like that, and theta is 45 degrees, let's say, as a result, for this special situation, I have to use a positive value of angle theta, because the right-hand rule tells me that the amount of that rotation angle is plus 45, is in the positive direction. But if I'm using this convention in here, in which case my thumb of the right hand is going to be pointing in the opposite direction. It's basically that picture in here, this picture in here, in which case I should describe theta as minus 45 degrees. Okay, just choose which one to use. So as a result, as long as you're consistently using the right-hand rule, everything would be okay. So this basically tells you that let's say a rotation theta around n, this is equivalent to a rotation minus theta around minus n. So again, there's an arbitrariness in the choice of the directions, but once you choose a direction, then you just describe the theta angle like that. Okay, so with this thing, I can actually write down a general expression of the rotation. So I'll just do it like that. So this time, this is the rotation axis. I'm going to think about a vector A, which may or may not be within that plane. Okay, so I'm going to decompose this vector A into these two components. Let me show them with a different color. Let's say one of them is blue. The blue one is, I'm going to call this as A parallel, and the other one is red, let's say. The red one is, I'm going to call A perp. So A parallel is essentially the parallel component of a component parallel to the rotation axis. So you can write it down like this. This is n times n dotted with A. These kind of expressions are valid even when A is a complex vector, but I mean, for the purposes of this thing, you just assume that this is a real quantity. So what is A perp? Well, A perp is it's basically the rest. So therefore, this is A minus n dot A. You can also think of it like that. This is actually minus n cross A, but these kind of descriptions might be a little bit more complicated than these. In any case, we are going to, of course, come back to that. So I know that vector A is a sum of the parallel component and the perpendicular component. And if I rotate the vector A, I know that the parallel component does not change, but the perpendicular component changes. So as a result, A prime can be written as the parallel component plus a rotated perpendicular component. And once I express this, everything will be all right. For this reason, let me just do this. I'm going to draw one more vector in here. So this is going to be a vector like that. The picture is not that perfect in here, but in any case, I'm going to choose this second vector as a vector which is within that plane which is perpendicular to the rotation axis. So within the plane where the rotation takes place, but it is perpendicular to that A perp in here. So it is quite easy to see that this is n cross A perp. So basically taking the cross product with n of this one is going to produce a vector which is perpendicular to it. So you can think of this as like a vector in the x direction, and this is a vector in the y direction. You can also think of it like that. In any case, so therefore, this is what I'm going to do. I can really see that the A perp prime in here can be written as cosine theta times A perp plus sine theta times n cross A perp. Right? That's also quite easy to see. So this component in here, I'm going to show this with a green color. Unfortunately, there are too many colors in here. So this is A perp prime. And we know that the angle between A perp prime and A perp is theta. The red and the yellow and the green vectors all have the same magnitude. So as a result, the magnitude-wise, there is no problem. But you can also see that, of course, the relationship between the A perp prime and the A perp and the other vectors is like that. So as a result, erasing all of these, I'm going to get this relationship in here. So let me write it down like that. So basically A prime is equal to the parallel component plus cosine theta times the perpendicular component plus sine theta times the n cross A perp. That's the relationship. What's the use? Well, of course, in some certain places where you need an exact expression for the rotated vector, you can use this. You can also try to compute the matrix elements of the rotation matrix by using this, by applying some specific vectors, for example. So in terms of the rotation axis and the other things, you can get these. But I'm not going to do this. I'll just do this. But I'm going to assume small rotations, right? Small rotations. In that case, that means theta is much smaller than basically the full rotation angle, 2 pi. And in that case, I'm going to expand everything to order. Let me first write down the exact expansion in here. This is theta minus theta cube over 3 factorial and then so on. There's this exact expression in here, but I'll just expand everything to order theta square. So as a result, we get this sine theta should be replaced with theta. What about cosine theta? This should be replaced by minus theta squared over 2, and higher order terms we just forget about. In that case, if I use these, I'm going to get this. So A prime would be basically A parallel that remains there. So I'm going to take this one. So that part would be theta times n cross A perp. Yeah, I should have also corrected this, but in any case, plus 1 minus theta squared over 2 times A parallel, A perp. All right, let me correct this. This one in here, n cross A perp. Well, that's the same thing as n cross A. There's no difference. So as a result, because the parallel component of A is already parallel to n, so therefore n cross that component would be 0. So you can easily see that this is that. I need some space for this. So as a result, let me just copy this and then pass to the next page. Right, let me correct this therefore. So I'm going to erase this perp sign in here, so this n cross A. There's still an A perp in here. So let's see. I'm going to separate this thing and then connect it with this one. So as a result, the first term would be A parallel plus A perp. There's a term which is linear in theta, which is this. And then there's a term which is quadratic in theta, which is that. Right? Let's just remember that there are actually higher order terms in here, so we are neglecting this part, but I'm also going to write them down. So you can see that this first expression is A. And the second expression is, let me handle this like that. So the third expression is theta squared. And I have said that a perp can also be written as negative of the n cross A. You just check this. You can easily say that this is the case. Now, that's an interesting twist in here. So in all of these, in both of these terms, you can see that the number of theta and number of n unit vector appear. They are the same. So we have 2 thetas in here, 2 n's in here. So let me erase this signs. So this then enables me to describe theta multiplied with n by some kind of a single vector theta. Okay. So this is going to be important because let's go back. There are actually 2 reasons for that. One of the reasons was that there was some kind of arbitrariness in the choice of n, so I could have chosen them like along plus n or minus n, but I had to use this convention. But you can see that as long as I use this convention, there is no difference between theta multiplied with n and minus theta multiplied with minus n. So somehow, if I actually multiply these, I don't have any freedom left in here. So as a result, I'm going to get the same vector in here. So basically I define a vector. I call this as theta. This is actually a vector in 3 dimensions. It has x, y, and z components. Somehow the magnitude of that vector shows the rotation angle and the direction shows the rotation axis. But there is no arbitrariness now for this kind of a thing. So that's the advantageous part. And one place where it appears that this kind of a definition is useful is this formula. So let me take this out and move it somewhere in here. All right, so that's in the corner. So you can see that in that case, the rotated vector is A plus this theta vector that I have just defined, cross A. There was these minus minus, which gives us plus, so that's 1/2 of theta cross A. And then there are these higher order terms. Now it appears that you can do this actually. You can also compute these higher order terms. So it appears that the next term would be 1/3 factorial times theta cross A. And you can see where this thing gets to is this is as if like this is a Taylor series expansion. I'm not going to show that this is the case, but you can easily verify this by yourself. So as a result, there is this n term in here where we have the cross product with theta n times. So as a result, we get like theta cross n. There are n times in here, n products. And the coefficient in front is equal to 1/n factorial. So as a result, this Taylor series expansion would be exact if it is summed to the all orders. So as a result, we have this kind of a notation for the rotation, for the action of the rotation of a vector, and we can express the final rotated vector in terms of the original vector like that. Okay, so we have a very nice expression like that. So as a result, I'm going to do this. So I'm going to use this notation. So theta, we have a vector theta whose magnitude is the rotation angle, right? And then this vector divided by its magnitude, that's the rotation axis. So if you do this, for example, in that case, you will always get positive rotation angles. But in any case, this is one nice situation. So as a result, for example, let's just do it like this. I mean, this is just as an example. Suppose that I would like to describe a rotation around the z-axis by 90 degrees, in which case I would describe, again, in all of these cases, I'm going to use this right-hand rule. So therefore, this vector would be plus pi/2, which is the rotation angle, multiplied with the z unit vector. So I'll just describe this rotation by a vector whose magnitude is pi/2 and whose direction is z. Or I can equivalently describe this as a rotation around minus z by an angle of minus pi/2. So that's going to give me the same vector. Unfortunately, things are not that easy. We actually still have some kind of arbitrariness in the choice of the rotation angle. So let's just remember that this pi/2 rotation, or plus pi/2, is equivalent to plus pi/2 plus 2 pi, which is also equivalent to, these are equivalent. So any rotation angle is equivalent to another rotation angle which differs from it by integer multiples of 2 pi. Okay, so let me write this correctly. So this is 5 pi/2. So somehow, therefore, a rotation axis, which is a rotation vector, which is pi/2 times z, this is equivalent to 5 pi/2 times z. I just keep this in mind. So there is this arbitrariness in here, but the arbitrariness is in the magnitude of the rotation angle. But sometimes people make this convention. So you can just assume that theta, the magnitude of the rotation angle, is always less than or equal to pi. And so by this convention, therefore, you can kind of uniquely describe all the rotations, except that for rotations with, I don't know, with angle pi, I can describe them with a rotation angle pi or minus pi. They are going to give me the same rotation actually. So as a result, let's say pi times z is equivalent to minus pi times c. In that case, I cannot make a choice between these two. In any case, there is this kind of an, basically, the notation does not give us a unique rotation vector because somehow the rotation angles can be described in many different ways. So as a result, the rotation angle vectors can also be described like that. Okay, so let's stop in here, but I'm going to continue with the properties of the rotation operators in 3 dimensions. Especially, I'm going to give you some kind of a relationship for the commutativity. And from here, we can also say something about the conjugacy relationship.